Electron affinity is like the opposite of ionization energy. It's the amount of energy, or the change in energy when a neutral atom becomes a negative ion. The electron affinity is usually negative, meaning that when you add an electron to an atom, energy is released. There are a few elements, though, where it's positive, and these are the alkaline earth metals and the noble gases. So a positive electron affinity means that you're basically having to pay the atom to take this electron. Why would the noble gases not want to take an extra electron? They're already stable. They're good. They're like, no, I don't need another electron. I'm perfect. Everything's good. If I take that extra electron, it's going to mess everything up. You're going to have to pay me a bunch of money to get me to take that. And the alkaline earth metals also do not want to take on an extra electron. The trends that we see in electron affinity are less regular than the other trends. There's a lot more irregularity in there. For the alkali metals, we do see a nice trend as we go down group 1. The alkali metals, as we go down, we see that the electron affinity decreases. But we don't see a trend like this in the other groups. It's just in group 1A. We can say that electron affinity generally increases, becomes more negative as we go across a period. But there are exceptions to this. For group 5A, we see that the ionization energy is lower than we expect. It's less negative. Remember, a negative electron affinity means that there's energy being released when you add the electron on. So that's something that's likely to happen. So group 5A wants that extra electron less than is expected because that extra electron is going to have to pair. So it's kind of the same reason that we saw that difference in ionization energy between 5A and 6A. And then we see that groups 2A and 8A, the alkaline earth metals and the noble gases have very low electron affinities because we're adding those into higher sublevels. The highest electron affinity in any period is going to be the halogen. Halogens are real excited about getting an extra electron because when they take on that one extra electron, then they have the noble gas electron configuration. So they're real stoked about that. So there is a general trend that electron affinity increases, becomes more negative as we go across. The way I remember that one is I think, well, if you compare lithium and fluorine, well, who's happier about getting an extra electron? Fluorine. Fluorine is really happy about getting an extra electron. So this is going to be more favorable. A negative energy change is more favorable. Fluorine is basically paying you to take the electron. You give it the electron, it gives you money, gives you energy. But if you try to make some sense out of those numbers, there's just a mess. Any questions about electron affinities? They're kind of in there, but I think the ionization energy stuff is a lot more important. This slide shows properties of metals versus nonmetals. And what we're going to talk about is metallic character. So when we talk about metallic character, we think, well, how much is it like a metal? Metals are malleable and ductile. You hit a piece of metal with a hammer and it doesn't shatter like glass. It just dents, right? They tend to be shiny. They conduct heat and electricity. Most of the oxides are basic. Those oxides, compounds with oxides, are going to be ionic compounds. Metals form ionic compounds. Metals form cations in solution, and metals are going to lose electrons in reactions. For the nonmetals, they're kind of the opposite. Nonmetals will form anions. They form polyatomic anions as well. And most of their compounds with oxygen are molecular, not ionic. You get a compound between nitrogen and oxygen. It's not an ionic compound, it's molecular. And the nonmetals gain electrons. So when we talk about metallic character, we're saying, well, how closely does this element's properties match those of a typical metal? And we see there's a definite trend here, and I think this is actually the easiest one to remember. Metallic character decreases as we go from left to right across the periodic table, and it increases as you go down. And it's much easier if we look at a picture. So if we're thinking metallic character, let's look at period 3. Here, sodium is a metal, magnesium's a metal, metal, semi-metal, phosphorus is a non-metal, sulfur's a non-metal, chlorine's a non-metal. It kind of tells you the trend. As you come across, they're going from metals to non-metals. Metallic character decreases as we go across. Aluminum has a lower metallic character than sodium does. As we go down a group, the top of the group here, group 5A, starts with nonmetals, nitrogen and phosphorus. Then it goes through a semi-metal and then gets into metals. So ionic character increases as metallic character increases as we go down. And there's another table that shows that. So if you remember this stair-step line, and these are the nonmetals, these are the metals, you can figure that one out pretty easily. Let's do a couple of these. On the basis of periodic trends, choose the more metallic element from each pair if possible. Let's look at germanium or tin. We're going to find them on the periodic table and see how they're related to each other. Germanium and tin. So on the periodic table, they're one above the other. Here's germanium, there's tin. We want the more metallic. So is the top one more metallic or the bottom? The bottom one, because we look at that group, the bottom of the group, those are metals. The top of the group is nonmetals. So the more metallic is going to be the tin. How about gallium or tin? Here's gallium and here's tin. Well, if we go across, that would say that it was gallium. And if we go down, that would tell us it was tin. Conflicting trends. So a reasonable answer is not possible. And we look at those, neither of them are identified on the periodic table as semi-metals or non-metals. And so I'm going to stick with the can't tell. So, not possible. How about phosphorus or bismuth? So here's phosphorus and bismuth is down there. More metallic, bismuth. It's on the bottom. And then boron or nitrogen. There's boron and here's nitrogen. These are both nonmetals, but one of them is more metallic than the other, the boron, because it's on the left. And as you go across, we start at the metals, and then it goes into nonmetals. Any questions?